Now let's talk about computing the HCF and LCM. Now, whenever we have to compute HCF and LCM, prime factorizations offers the prime factorization this offers the fastest way of finding both the HCF and LCM, and that too simultaneously. Now let's look at finding both the HCF and LCM of numbers 8, 36 and 40. Right? So what I'll do is I'll write down 8, 36, 40 and I'll write down their prime factors. So 8 is 2 cube, 36 is 4 into 9, which is 3 square, and 40 is 8 5 the 40, right? So 2 cube multiplied by 5. Now notice the way I've written these. The way I've written these is I've kept all the factors which comprise of 2 and its powers below each other. Then I've kept all the 3's one below the other, and I've kept all the 5's one below the other. This is just to avoid confusion, right? So now what I'll do is I'll write HCF here and LCM here, and I'm going to figure both of them out simultaneously. Now for HCF, just look out for all those factors which are common across all the three numbers, right? So if there were 4, then you'd look out for all the factors which are common across, the prime factors which are common across all the numbers. Now here, I notice that 3 is not common across all of them, 5 is not common across all of them, only 2 is, so I'll write a 2 here. Then I will go ahead and select the lowest power of 2 across all of these three numbers, and I notice that the lowest power of 2 is 2. This is my HCF. Okay. Now for LCM, I'll write all of these numbers. So if 2 has occurred once, then I write 2. 3 has occurred even once, I write 3. And if 5 has occurred even once, I write 5. So I write all of the 2 and 3 and 5 here. And now I pick the highest power for each. So highest power for 2 is 3. Highest power for 3 is 2. And highest power for 1 is just 1. Right? So what we get, HCF, 4 and LCM is 2 to the power 3 multiplied by 3 squared multiplied by 5, right? So I get 8 5 the 40 and 40 into 9 360, right? So this is what my LCM of these three numbers will look like. Now there's another way of finding out HCF, and that's called the Euclid's method. Now in Euclid's method, and this method is particularly useful if, let's say, I get a pair of numbers which are not, whose prime factorization is not exactly the easiest, right? So let me take an example. The example I take is 221 and 481, right? So not the easiest numbers to probably factorize, right? But in Euclid's method, what it does for me is it's very straightforward. So what I'll do is I'll start dividing the larger number with the smaller number. So I'll divide 481 by 221. Now 221 times 2 is 442. This leaves me a remainder of 39, right? Now what I do is I bring this divisor and divide this divisor by the remainder. So now I am dividing 221, this number, by 39, the remainder from the previous computation. Now 39 times 5 gives me 195. Now the difference between these two numbers is 26, right? So now I do this the same method again. So just like I brought 221 here and divided by the remainder of the previous computation, now my remainder is 26, and I'm going to divide this divisor 39 by 26. So 26 won the 26, and I'm left with the remainder 13. Now I do the same thing and I bring 26 down. Now 13 times 2 gives me 26, and there is no remainder left, right? So as soon as there is no remainder left, the last divisor using which I've got a 0 remainder is the HCF, right? So a fairly straightforward method of computing the highest common factor if we figure that these two numbers are a little difficult to factorize. right? So you will use these two methods most commonly in finding. This method will help you find the HCF and the LCM. This method will help you find the HCF, but then we can use this method in conjunction with other methods that you'll study later on to find even the LCM.